Okay, everyone, let's get started. Hopefully this will be a short lecture today. My plan is to talk about the final project, and then we'll give the course surveys out. So first of all, are there any issues with Lab 5? Any major problems? Okay, so that one's due tonight, and then today I'm going to assign the final project, which is Lab 6. Our next class, a week from today, is our last class, and we will meet in the teaching lab for that. So this will be our last class in this room. The final exam is on May 6th at 4 o'clock, 4 to 6:30, although I don't expect you'll need nearly that much time. The final exam, as I mentioned at the beginning of the semester, is designed to differentiate partners in groups where one partner is doing almost all the work. So if you've been working on the projects, the final should be pretty easy. I'm just going to ask some short questions about memory mapped I/O. That's where you load or store to certain memory address regions to talk to hardware. Bare metal programming concepts. The idea that you're writing code that doesn't run on top of an operating system, so if you crash, then it just bricks the system, that kind of stuff. Floating point versus fixed point, and understanding fixed point arithmetic and how it works. If you add two fixed point numbers, you have to make sure that the radix point, the decimal point, is aligned. It's in the same bit position. If you multiply two fixed point numbers, the number of fractional bits in the product is the sum of fractional bits in the two operands. Performance analysis, CPI, instruction count, clock frequency, how you measure performance, how you use a performance counter to measure a cycle count before and after the code that you're measuring runs, and that kind of stuff, and take the difference. Basic stuff about image transformations, how those work. So the ones that we use, we just iterated through all the pixels and then multiplied each of the row and columns by a 2x2 matrix to get the transformed locations. Maybe a question about the Mandelbrot set, and then addressing, consecutive addressing versus XY addressing. Basically how you take a two-dimensional frame or an image and overlay it on top of a one-dimensional memory array. So those are the kind of questions I'll ask. If you have any questions about that, let me know. Yes?
Is there going to be a study guide that just kind of goes over these, just some general facts to remember going into the test? Or?
I don't have one written up yet. I was planning on sending out an email with a little study guide. But those are the topics.
Yeah. Okay.
Yes?
So myself and a few others are a bit concerned that the final project and the final exam are on the same day.
Well, the final project, so I like to give everyone as much time as possible to do the final project, especially since I have a really lax late policy. So some of you might have gotten caught up with other projects and other classes and decided to turn in some of the earlier projects later, so you might have got behind. So I want to give you as much, and also this is a senior level course, I think, right? Most of you are seniors, so I think this might be the last semester for just about all of you. So I know you've got other things going on, so I try to give you as much time as I possibly can to do the final project. So it's due on May 6th. You can obviously turn it in before that, and I would hope that you turn it in sometime before the end of next week. But you don't have to demo it. We're just looking for a submission. And also, as I'm going to explain here in a few minutes, the final project is really kind of a minor enhancement over Lab 5. We're just going to take Lab 5 and convert it to fixed point, basically. So there's not too much work involved. I'm trying to make it as easy as possible on you. If you've got Lab 5 working, then hopefully Lab 6 won't be too much trouble. Okay, any other questions? Okay. Yeah, and you know, the lab being due on May 6th is because they want us to get the grades in, I think, 72 hours, no later than 72 hours past when the final exam is scheduled for the course. So it just gives me barely enough time to grade it. Okay. If you need a little extra time, I can try to accommodate you, but pretty much I'm going to try to push this out as far as I can. Okay, so the final project, as I mentioned, we're going to begin with Lab 5. So you'll have to have Lab 5 working. And we're going to convert all the floating point in Lab 5 to fixed point. So this is similar to what we did with the image transformation code. The only difference is that with the Mandelbrot set, we want to maximize the precision. Okay, so what's the deal with that? Well, currently you're all using floats, right? Single precision floating point. So that gives you how much precision? Anyone remember that?
32 bits. Like according to the last lab?
Yeah. Well, the floats are 32 bits in total, but not all of those bits are used to store the value. Only 23 bits are used to store the value. The other 9 bits are used to store essentially the exponent, which is where the decimal point is at, is the floating position of the decimal point, or radix point. And then there's a sign bit. So 9 bits are kind of miscellaneous, and 23 bits are used to store the value. With a fixed point number, we could possibly use all 32 bits for the value as opposed to only 23 bits. As you know, with float, we're essentially using a 23-bit number, right? So with a fixed point number stored in an integer, we might be able to get 9 extra bits of precision, possibly, right? Make sense? So what does that give us? Well, it allows us to zoom another 9 zoom levels, essentially. I don't know if any of you have looked at any of the videos online on YouTube where people have done Mandelbrot sets and zoomed in really far. And when they do that, they're using really big numbers to represent those values. Because the idea is that you need precision, because when you're calculating a Mandelbrot set, you need to be able to differentiate one pixel's value from the one next to it, right? And as you zoom in more, that difference between those 2 pixels becomes increasingly smaller. So eventually, you'll get to the point where there's no standard data types that have enough precision to work. So the videos on YouTube are like, they're using insanely large numbers. They're using multi-precise arithmetic. So they're doing like 1,000-bit numbers or 2,000-bit numbers in order to in order to continue to differentiate pixels as they keep zooming in to, really far, right? Does that make sense? Okay, so we want to begin with Lab 5. We want to convert all the floating point to fixed point. Hopefully this will speed things up significantly. And we want to compare the CPI and instruction count of the innermost loop. And in this case, I'm going to make it easier on you. Another way to make it easier on you is you only have to do this for the 4-processor version. So in Lab 5, I asked you to measure the performance for 1, 2, 3, and 4 processors so you can see the impact of scaling up the number of processors. But in this lab, we want to compare fixed point to floating point, so there's no point in trying different numbers of processors. You can just go with 4. Okay, yes?
So I have a question. When printing in a frame, when it's, at least on my program, when it's zoomed in, I think +3 or +4, when most of the screen is black, let's say that I zoomed in at a specific place in the picture, it's actually printing way faster. All the black pixels are printing way faster.
The black pixels should be printing slower because those are the ones that max out the iterations, whereas any pixel that's not in the Mandelbrot set bails out early, so it doesn't go through all of the trips of the while loop. So if it's in the Mandelbrot set, well, it depends what you mean by black, though. If it's black because it's in the Mandelbrot set, those should be slower. If it's black because it's kind of outside the Mandelbrot set and it has a very low,
Inside,
if it's in it, okay.
Like, right in the middle of the picture, when it zooms in where, like, let's say the right side, like only the right top part of the screen is, like, let's say green or blue,
Mhm.
whatever color, and then the rest of it is black. It prints it slowly. Once it gets to all black, it just speeds up and prints everything at once. And that's for the 1 and 2 processors.
Oh, okay,
Because
that's
I
interesting.
can explain why that would happen.
Yeah, normally it's the frame time, the time it takes for a frame varies wildly depending on how many black pixels are in your frame. That's why I asked you to measure the innermost loop, the while loop, so because that's kind of the kernel, that's the main,
Inner while loop.
the innermost while loop. So not the 4i, not the 4j, but the one that says while x squared plus y squared is less than 4 and iteration is less than 500. That's the bottleneck, right? The speed of that innermost loop. That's what you want. If you make any improvement to that innermost loop, it's going to make a huge overall improvement.
Okay, I
Right.
actually got it just, okay. All right, I had a little bit of problems with that anyways, and then I don't remember if it was actually a dual while loop or if I converted it to a dual while loop, but I played around with it a lot.
Well, some people use while loops for the pixel
I'm talking
loops
about,
too.
like, the inner, most
Yeah.
inner one. I believe
Yeah.
it was a while loop and I converted it to a dual while, or the opposite or something. I did something with it.
Yeah, you could do a for loop too if you wanted to. I call it a while loop just because it's a while loop in my pseudocode. But yeah, I mean the innermost loop, the iteration loop that goes through, and specifically it's the loop that calculates the polynomial, the Mandelbrot polynomial, P of z equals e squared plus c, the loop that does one evaluation of that polynomial. That's what I'm talking about. That's the innermost loop. Okay. Okay, so what are we using fixed point representation for? With the image transformation code, it was a little confusing because the sine and cosine calculations had to be done as floats, and then you had to convert those to fixed point, right? So there was no way to actually convert the entire image rotation code to purely fixed point because you always had that sine and cosine, right? So I think most of you did that calculation outside of the for loops, right? You just did that once per frame. And so that way, if you look at the execution time, very little of the execution time was doing floating point stuff. With the Mandelbrot set, if I'm not mistaken, you don't have to do any floating point at all. Like, you can completely eliminate floating point from the entire program. So we need a fixed point representation for 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 9 or so variables in total. We've got z, which is the imaginary number that is the output of the polynomial, which in my pseudocode I call x and y. Then there's c, which is the imaginary representation of the pixel, right, which is x0, y0. So there's x and y and x0, y0. Then we've got min x, min y, max y. And then there's x squared plus y squared, which is a value that you calculate only for the while loop, right? So that's the sort of the vector norm of the imaginary number. Well, the square of the vector norm. Technically, to do a norm, you would have to take the square root of that, right? But we get around that by comparing it to 4. You guys with me? Okay, so you want to do all that in fixed point. So recall that the fixed points have fixed range. That's why fixed point is kind of obscure, because whenever you use fixed point, you have to worry that what your range of values that you want to represent with it, right? Now you might say, well, wait, technically floating point has a range too that you can't go outside of. You can overflow or you can underflow a floating point number. That's true, but floating point numbers have a huge range. Fixed point numbers have a range that is defined by where you fix the decimal point, or like I said, radix point. Technically, decimal implies base 10, but the dot, right? So you have to decide where the radix point goes, and that will give you a range. Okay. So for regular integers, the range is, if it's signed, it's -2 to the n minus 1, where n is the number of bits. So 2 to the n minus 1 to 2 to the n minus 1 minus 1. So if it's a 4-bit number, it would be -2 to the third, -8 to +7, right? If you have a fixed point number, now there's really no standard way to describe a fixed point number. The way I always did it was an nm number, where n is the number of bits, the total number of bits, and m is the number of fractional bits that come to the right of the decimal point. I think that's the easiest way to describe it. So if you have like a 4-bit number, say, and 2 of the bits are fractional, you're basically just splitting the number in half, where 2 bits are on the left-hand side of the radix point, those are your integral bits, and 2 bits are on the right-hand side of the decimal point, the fractional bits, the radix point, right? So in that case, the range becomes -2 to the n minus m minus 1. So what that means is, if it's a 4-bit number and 2 bits are fractional, the range would be -2 raised to the 4 minus 2 minus 1, right? So -2, right? Make sense? -2. And then the upper end of the range would be also -2, but just under -2, because you have to subtract whatever the significance of the unit in the last place. So in this case, 2 to the minus m, that's 2 to the minus second, that's 1/4, right? 1/4, right? So the range in this case would be -2 to +2 minus 1/4, so 1.75, right? You guys with me? Make sense? So what's the point of all this? The point is that you've got the same number. You can start out with the same number of bits, but depending on where you put that decimal point, the range is going to be altered, and specifically, it's going to be essentially determined by the number of bits that are on the left-hand side of the decimal point, right? The non-fractional bits. Everyone with me? Okay, so in this lab, we're going to use integers, 32-bit integers, for your values, all your values. Signed. We'll use signed. Just to simplify, not everything is going to be signed. Obviously, when you do x squared plus y squared, that's always going to be a positive number, right? So that could be unsigned. But to simplify things, let's just assume everything's signed, okay? Because we know that z can be negative, and x and y can be negative, and x0, y0 can be negative. A lot of these things can be negative, so we'll simplify things and we'll just treat everything as signed, okay? Okay, so here's the problem. I'm kind of embarrassed to say, I don't have a great methodology to figure out where to put the decimal point. I really don't know how to do it. I came up with this kind of ad hoc method. The idea is, the idea is we want to have as many fractional bits as we can get. The more fractional bits that we get, the more precision we're going to have, and the farther in we can zoom. So we want to maximize the use of every bit. We don't want to waste any bits. So we want to select our decimal point location such that it is the farthest to the left to accommodate all the numbers that can possibly come up during this program, right? So we want to have enough range to accommodate all of these extreme values, either on the negative side or the positive side. You guys with me? right? So we want to find out basically was what is the largest value that we can get while we're running the Mandelbrot set? What's the biggest values we can ever see? And then we just need to leave enough non-fractional bits to be able to store those numbers. Okay? So how do we do that? Well, the problem is that we've got several values. We've got z. Again, z is x and y in my pseudocode. You might have named it something different. Charles, one of my students, when he took this course, he created a struct to store, x and y. That way he could create something actually called z, and then he could say z dot x and z dot y, right? But I'm too lazy for that. I just use x and y and x0, y0. Anyway, so z is x and y, c is x0, y0 in my pseudocode. And so I looked at kind of the extreme, I tried to pick extreme values. I tried to essentially take a circle with a radius 2, because you know that the Mandelbrot set is contained within a radius 2 circle of the origin, and you would never start out with a c value that's outside that range. What would be the point, right? There's no point in doing that, because we initialize the program with that radius and then we zoom in. So let's say z is 0, 2, right, which would put us 0, 2 kind of at the top of the circle, right? And let's say c is 0, 2. So, and that makes sense, because z would start out at 0, so if c were 0, 2, the first z value would also be 0, 2, right? Because the first thing you do is you add, right? The first thing that happens is z starts out as 0, and you put c in as z on the first iteration of your while loop, right? So if you did that, you calculate the new z value, and it will be, now remember, the new z value is x squared minus y squared plus x0, right? And the imaginary component is 2 times x times y plus y0, right? According to the code, right? So this is basically squaring z, adding c, right? But doing it with each of the components separately, right? And if you do that, the z value is negative 4, 2. Now you might say, wait a second, that's outside the circle. Yeah, but remember, you have to allow the possibility for the z to go outside the circle in order to be able to detect that it's outside the circle, right? So you have to leave enough range for that. You guys with me? So how many bits would that take to store that value? Well, that part's kind of tricky, actually. How do you figure that out? Well, you might say, okay, well, 4, the square root of 4 is 2. But actually, if I want to represent the value of 4, I need to have 3 bits, right? Remember, 4 in binary is 1, 0, 0, right? That's 3 bits. And you have to add a 4th bit for the sign, right? So that's actually 4 bits I need on the left-hand side of the radix point. Does it make sense? Positive 4 requires, in a signed number, requires 4 bits. But here's where it gets crazy. The only way for me to know that that's outside of the radius 2 circle is to calculate the norm. So if I take negative 4, 2, and I take x squared plus y, or x0 squared, oh wait, that's screwed up, sorry. Sorry, that should say zx squared plus zy squared. There we go. Okay, so if I take the norm, so I go back to the z, and I look at I calculate the norm of the imaginary number, I'm actually going to get 20, right? Because that's going to be 16 plus 4, right? So how many bits do I need to store 20? I actually need 7 bits, because 20 is 1, 0, 1, 0, 0, right? Did I get that right? Oh, I screwed that up, didn't I? Do I have a marker? So 20 is going to be 16 plus 4, like that, right? Right, so this is, make sense? So that's 1, 2, 3, 4, 5 bits, plus the sign bit's 6. So that should actually say 6 there. All right, so sorry, I screwed that up. It doesn't matter because I'm going to need 7 for one of these other examples, but yeah, 6, sorry. See, I second-guessed myself. It did say 6, and I changed it just like an hour ago to 7. For some reason, I thought it was 7. Okay, how about this one? If z is negative 0, 2, and c is 2, 0, is that ever going to happen? Probably not, but let's just say it does. That's going to give me actually a pretty small number for both z and the norm. But here's an extreme example here. Let's say I'm at negative 1.5, 1.5. So this is based on the notion that if I am up here, right, if I'm on the 45-degree angle on the unit 2 circle, that would be the square root of 2, right, would be x and y. So the square root of 2 is 1.4 or something. I round that up to 1.5. So let's just say I'm at 1.5, 1.5, which technically is outside that circle, right? But I rounded the square root of 2 up to the next 10th, right? So if I have 1.5, 1.5, let's say c is the same thing, I end up with a vector norm of 38.25, if I did that right. And so I need 7 non-fractional bits, right? Because 38 is going to be 32 plus 6, so 110, like that. Yeah. So this is going to be 38, right? So that's 1, 2, 3, 4, 5, 6, 7 bits with the sign bit. So that's, I think, I've never been able to come up with a scenario where I need more than 7 non-fractional bits. But then again, I'm not doing a full exhaustive search here. Mostly because I really don't know what combinations of z and c are possible, really. Right? I mean, I'm trying to look at like extreme values, but I don't know all the combinations that I need to evaluate. I don't know how to do this. I'm just trying to pick, you know, sort of these, the highest, the biggest, the largest magnitude numbers that I can come up with. And I can't find any examples where I need more than 7. Right? So I think that's the right answer. I might be missing something here, but I think that'll do it for us. So I think to be safe, I think we should be safe with 7 non-fractional bits. So that means that if I have a 32-bit number where 25 bits are fractional, that should cover me for fixed point. So that'll give me, that's actually going to give me 2 more bits than floating point in terms of precision.
I thought we didn't have any negative numbers.
You can have negative numbers. I mean, you can have...
The imaginary number could be negative, but I mean, we're only taking the absolute value of the negative number anyways.
Well, you can have a negative number if you're evaluating it and you want to zoom in on something, or you're going to have a lower left-hand quadrant, right? Those are going to be negative real and negative imaginary, right? So that'll be your c value, right? And then when you do the while loop, you're calculating a z value. So those can all be signed, right?
Did we create a struct where it has like the actual number and a decimal? So it has 2 ends, the actual and a decimal, and then
you could
like unshift.
Yeah, you could come up with your own format, and then I think that's what those people do that do those really crazy ones on YouTube where they zoom in. The problem with that is it's going to be really slow. So because you have to come up with, basically the reason that's going to be slow is every time you do an add or a multiply, it's going to take multiple instructions, right? If we do it with 32 bits, The advantage is every operation we do is one instruction, which is the fastest that Neos processor will go, or any processor will go, is if you're doing native instructions. Once you start doing, this is why encryption and decryption is slow, because when you do encryption, you're dealing with big numbers too, big 512-bit numbers. So it's expensive, right? In this case, we want to optimize for performance, so this is essentially kind of the fastest you can get with the most precision you can get, this is the Pareto optimal solution, where you're trying to optimize both performance and precision. I think it's the best I've come up with, right? I think if you start splitting and coming up with your own representations, that's fine, but it's going to be ungodly slow on the microblaze, unless you were to come up with custom hardware on the FPGA, but we don't cover that in the course.
Thank you.
Okay. Any questions? Any other questions? Okay, so that's going to be 32 total bits, 25 bits that are fractional, 7 bits that are non-fractional. The problem that comes up with this is when you multiply two numbers that have 25 fractional bits, the product is going to have 50 fractional bits. Now, when we did the fixed point with the image transformation lab, this wasn't a problem because we only had 8 fractional bits, and so we could multiply the numbers and we got 16 fractional bits, but we still had plenty of space on the left-hand side of the radix point where we didn't have to worry about trying to preserve, in other words, we only kept whenever we did a multiply, we only were concerned about the 32-bit result of the multiply. You guys follow that? Does that make sense? I'm not explaining that very well. So if you multiply two numbers normally, if they have n bits each, the result of the multiply really ought to be twice as many bits as the operands, right? So if I multiply two 32-bit numbers, I really should have a 64-bit result, right? But with fixed point, it's a lot more important, because in this case, if I have two 32-bit numbers with 25 fractional bits, I multiply them. If I only keep the 32-bit product, then I'm actually going to be missing out on all of the non-fractional bits in the product, as well as some of the fractional ones. Does that make sense? Because I should be getting 50 fractional bits from the multiply. But if I only keep 32 bits from the product, I'm losing a lot of information. In fact, there's really no way to recover from that. I have to keep, I need at least all the fractional bits from the multiply. You guys with me? Right? So anyway, basically what I'm saying is you need to have all 64 bits of the product. So the question is, does the hardware support? Does the hardware support this? Yeah, the hardware supports this. The multiplier in the Neos processor will give you a 64-bit result if you need it. The problem is convincing the compiler to give it to you, right? Because the compiler, whenever you multiply two integers with a compiler, if you're not careful about the types, the compiler may just give you the lower 32 bits of the product. Does that make sense? Right? So if you have two integers and you multiply them in C, most oftentimes you'll just get a 32-bit product, right? But we want to tell the compiler and the hardware that we want to multiply two 32-bit numbers and we need the full 64-bit result. So how do you do that? You just have to be careful with the types, like I said. So for example, if you've got A and B are your two operands, those are the two numbers you're multiplying, if you typecast those, even if they're declared as 32-bit numbers, alt32, or integers, just plain ints, right? If you multiply those, make sure you typecast them as an alt64, or as a long, which sounds ridiculous, but that's actually a type long. Altera has a more precise type that does the same thing, but it's more precise. Alt_64, right? So if you typecast the operands as Alt 64, not U64, just Alt 64, and you put those into an, now here's the part that's hard, that you have to make sure you get right. You have to put the result into a variable that has been declared as a Alt 64. Does it make sense? And if you do that, it should preserve all 64 bits of the product. Now, the first thing you want to do after that is you want to shift it and get it back into 32 bits as quick as you can, because the longer you keep it as a 64-bit number, the more expensive it is to do. You're not going to be able to do single instruction operations with it as a 64-bit number, as a 64-bit operand. You guys with me? So what I'm saying is the multiply, where you take two 32-bit numbers, multiply them and get a 64-bit number, that's a one instruction operation. But once you've got a 64-bit operand, from that point on, you can't do single instruction operations to it anymore, which is why you're going to want to shift it 25 bits to the right? So you want to readjust the decimal point right after you multiply. You guys with me? Now you might say, wait a second, when am I multiplying two fixed point numbers? Well, when you calculate the polynomial, which is z squared plus c, right? Whenever you multiply your x's and y's together, right? Okay? So just be careful about that. You don't want to truncate. You want to make sure you keep all the bits from the multiply. Any questions about that? Now again, this wasn't a problem with the image transformation because we had so few fractional bits that we didn't worry about it. We had, like with the image transformation, you remember with that, we only had 8 fractional bits, and we had plenty of non-fractional bits, much more than we needed, because we were only dealing with 8-bit color values. Well, with 8-bit color values, you've got some flexibility inside that 32-bit variable, right? But now we're pushing things to kind of an extreme. We're dealing with very large numbers because we've got so many fractional bits, right? Okay. Alrighty. Okay, that's all we've got actually. So that's the kind of the description. The lab sheet is here. I've got this posted on the website. Convert your solution for Lab 5 into fixed point, eliminating all the floating point types and operations. These 4 requirements are the same as for these 4 performance measurements are the same as for Lab 5, except you only have to do them for all 4 processors. So we want to know the average time to generate each frame over at least 4 frames. Why over 4 frames? Because, like we were talking about earlier, the time per frame is going to vary depending on how many of the pixels are in the Mandelbrot set. So we want to do it like an average. And then the average number of clock cycles to compute and paint each pixel over at least 1 frame. The number of cycles to compute 1 iteration of the polynomial evaluation loop. And the number of cycles per floating point op. So this is not something you have to measure. This is something where you essentially take this number 3 and you divide it by the number of operations. And when I say floating point, I mean floating point or fixed point, depending on which one you're doing. Yes? Okay, yeah, so that's a little unclear. Main arithmetic operation, right? And we want to compare to Lab 5. Now you guys have already done this with the image transformation code, and hopefully you discovered that the number of instructions, you counted instructions before, we're not counting instructions this time, but I think most groups concluded that the fixed point requires more instructions. Why? Because there's shifting and stuff involved, right? There's more maintenance you have to do with the fixed point numbers. But the cycles per instruction is much less than for floating point, because every floating point op takes like 5 to 10 cycles. whereas integer instructions are 1 cycle. So,
Actually, GDB shows, I don't know what I added, but I added the command in GDB, and it shows you all the instructions all the other classes that the float calls, so it's more instructions, at least in my case.
for floats?
Yeah.
Okay. Well, that might have been because some of the floating point instructions whenever you're doing typecasting, like we had to do typecasting, you waste a lot of instructions typecasting too, because I don't think there's hardware support for some of the typecasts in the Neos. Some processors do. Like I think Intel has hardware. Like if you do a typecast in an Intel processor, I think it can do it in 1 instruction. But the Neos, I think sometimes they're still calling those routines. So another advantage of fixed point is you don't have to worry about typecasting. You are converting between floating and integer. But anyway, in this case, we have a little bit more overhead because we have to do the shifting still. Anything else? I guess it's still just shifting. Yeah, it's the main overhead with fixed point. But we're not counting the number of instructions, but the number of cycles hopefully is less with fixed point, and hopefully we should be able to zoom in a little bit further. So we should get 2 wins out of this. We should get more speed and more precision and a deeper zoom. Okay? Any questions? Now, I've left out one thing here. The min and max x and y, you have to keep that in fixed point too. So there's a little bit, make sure you also include that when you do your conversion, fixed point conversion.